Cisplatin is used as an anti-cancer drug. Cisplatin works by causing the death of rapidly dividing cells. Name the process that is prevented by cisplatin during cell division. Cisplatin causes DNA to kink and prevents DNA replication. After cisplatin enters the cell, one of the chlorides is replaced by a water to form complex B. Give an equation for this reaction. So we've been given cisplatin's formula at the top, and we've been told that one of the chlorides is replaced by a water. So we're going to replace one of the chlorides, so leave the two ammonias, now have one water, keep one chloride. Now because we've removed a Cl-, the complex will become positively charged, and we've written an equation. When the complex B reacts with the DNA, the water molecule is replaced by a bond, as a bond forms between platinum and nitrogen in guanine. The remaining chloride ion is also replaced, so we'll have ended up replacing the chloride and the water. We'll still have the two ammonias, and that happens between another guanine. So figure 1 represents two adjacent guanine nucleotides in DNA, complete by showing how the platinum complex forms a cross-link. So you have to sort of have an awareness of the structure of guanine and how it's working, and you do need to know, remembering that these three atoms are the three that do the hydrogen bonding to cytosine, which then means that we're looking for the nitrogen atom that is able to make a cross-link. So is it open and available? And so we're looking for the nitrogen that is in the free part of the chain, these two that I've circled in blue. So I'm just going to get rid of those circling because that's not part of our answer. We're going to take those two that were in blue. Now they're using a lone pair, but they're using it to form a coordinate bond. So I'm going to represent that by an arrow. And then we've got the two bonds to nitrogens in ammonia. And there is our cross-linked guanine and cisplatins. An experiment is done to investigate the rate of the reaction in question 4.2, that was the hydrolysis reaction. During the experiment, the concentration of cisplatin is measured at 1 minute intervals. So we're measuring concentration against time. Explain how graphical methods can be used to process the measured results to confirm that the reaction is first order. So we would plot concentration against time. And then cisplatin was a reactant, so we would get this kind of like curve coming down. What we would do then is take tangents at various times and find their gradient. This gives rate at different times. Then what we would do is plot rate that we've got from our gradients against the concentrations that we had at those times. So we'd have rate against concentration. And then if it's first order, would be a straight line, and we can't just say a straight line because a straight line could be zero order if it was horizontal. So we have to say a straight line through the origin. And that is how we would confirm it was first order. In another experiment, the effect of temperature on rate in question 4.2 is investigated. Table 1 shows the students' results. Complete table 1. So the first thing we have to do is do 1 divided by 318. So if on our calculator we do that, we write our results consistently with the rest of the data in the table. We get 0.00314. And then the other gap is ln of little k, the rate constant k. So we're going to natural log 6.63 times 10 to the minus 7. We get minus 14.2, and that does seem to fit in line with the other data. So that it sort of makes us feel that it's probably right. The Arrhenius equation can be written in the form ln k is minus EA over RT plus ln A. Use the data in table 1 to plot a graph of ln k against 1 over t. So they've given us the 1 over t scale from 0.00310, where our first reading is, to 0.00350, which encapsulates our biggest at 0.00341. But they haven't filled in the ln k scale, and we need to go from minus 13.6 to minus 17.7. So we want to make a scale, looking at what they've given us. If we started at minus 13 on the big square, minus 14, minus 15, minus 16, minus 17, remember we need to get to minus 17.7, minus 18, then it does seem to fit to the graph paper quite nicely like that. So we're going 13.6 at 0.0310, so that's actually on the axes. Then we've got minus 14.2 at 314. So minus 14.2 at 314. Minus 14.9 at 319. 14.9 at 319. Then we've got 16.3 at 330. 16.3 at 330. And then 17.7 at 341. We have all our points plotted. We now need to put our ruler on our graph and draw a line of best fit. So equal number of points above and below if they're not exactly on the line. So I'm just going to do that again because it's just a little bit too high. Feel that that is nicely done now. And we've got to use this graph to find the activation energy. So to find the activation energy, we've got to remember that the gradient is this part of our expression. So the gradient equals minus EA over R. So let's find the gradient. So we can see that it crosses through our points. So we have minus 13.6 at 0.00310. And then we've got the very bottom here at 0.00343 and minus 18. So our change in Y is minus 4.4 divided by 3.3 times 10 to the minus 4. And so I'm getting minus 13333. And the exam board are allowing anything between 12,876 and 13,598. So I'm within their range. Okay, so the gradient is negative and minus EA over R equals that number. So minus EA equals, I'm going to times this by 8.31. Which is minus 110800. So activation energy equals 110800, but that would be in joules per mole because the gas constant is in joules per Kelvin per mole. So if we divide that by 1,000, we get 110 or 111, round up, kilojoules per mole. So anything between 107 and 114 is in range.